Okay, so let's do now shortest paths in a DAG. DAG is a directed acyclic graph. So So this actually motivates what we're going to be doing on Monday, which is finding topological sorting, or finding an order of the vertices in a DAG such that there are no paths from vertices with larger labels to vertices with smaller labels. So in a DAG, you can order stuff such that, well, all the edges go from things with smaller labels to larger labels. So this is topological sorting. Suppose that we have figured out how to do this on Monday, and we topologically sort the DAG. So we have some DAG. So maybe we have some edges. Okay, so this is kind of ugly. Let me just take that out of there and put it in here instead. So let's just do that, and let's just do this. Okay, so we can topologically sort the vertices, so that will give us some ordering like this. So all the arrows go from, if an arrow goes from I to j, then I is smaller than j. Possibly, yeah, you can't have self-loops, I think, in a DAG, because those are cyclic. So notice that this actually isn't the only ordering like that. I could swap 1 and 2, and it would still be a valid topological sort. So let's put some distances on here. Let's say this is 3. No, let's say that it's going to be roughly proportional to, let's say this is 9, this is 2, this is 2, this is 4, this is 1, 5, 6, 4, 9. Am I missing any edges? Yes. 1, 3, 1. Okay. So now suppose we ask, what is the shortest path from vertex 3 to everything? Okay, well, you can't get from 3 to 1 or 2, because if you could, it wouldn't be a valid topological ordering. Okay, because we said that all the edges go from things with smaller labels to things with larger labels, so there's no way to get from 3 to 2 or from 3 to 1. So if we ask what is the distance from, okay, well, we can just draw this as yeah, let's do this as a table. So if we say 1, 2, 3, 4, 5, 6, 7. Okay. So what is the distance from 3 to 1? It's infinite. What is the distance from 3 to 2? It's infinite. What is the distance from 3 to 3? It's 0. Okay. So now it gets, this is where the algorithm comes in. to find out the distance from 3 to 4, we're going to work through the vertices in order. And for each vertex, we're going to look at its predecessors. We're going to take, and over each predecessor, we're going to take, for each vertex V, min and for each predecessor u of v. So that means vertices such that there's an edge from u to v. Okay. Take min. Okay, I shouldn't write it that way. It's going to be, I should write it like this. Min over dist 3 to u plus dist u to v. U is a predecessor of v. Okay, so this is how we're going to think about this. So okay, actually this works even here because we can say 1 has no predecessors, so we take the min over an empty set, and we're going to define that to be infinite. 2 has no predecessors, so we're taking minimum 1 over an empty set. I guess you would set all of these to be infinite first, and then you run this code. 3, well, distance 3 to itself is 0, okay, fine. 4, okay, so now we look at the predecessors of 4, it's only 2. And so we say, okay, distance from 3 to 2 is infinite, plus distance from 2 to 4 is 2, so infinite plus 2 is also infinite. And then, okay, so let's look at 5. Well, the predecessors of 5 are, what are the predecessors of 5? Well, the edges coming into 5 are from 4 and from 3. So we take the minimum of distance 3 to 3 plus distance 3 to 5, which is 0, plus 1, so it's 1. And distance 3 to 4, which is infinite, because we have it in this table already, plus distance 4 to 5, which is 1, so the distance is 1. So now let's take 6. What are the predecessors of 6? 3, 5, and 4. And so it's min of dist 3 plus dist 3, 6, dist 3, 4 plus dist 4, 6, dist 3, 5 plus dist 5, 6. So this is 0, and this is 4. This is infinity. This is 5. And 3 to 5 is 1. It's 1, and 5 to 6 is 3. So this is 4 in 2 ways. And then 7, okay, is min. Okay, what are the predecessors of 7? 1, 5, 6, and 3. So it's min dist 3 plus dist 3, 7, dist. Okay, sorry, I should have put dist 3, 1 plus dist 1, 7. Dist 3, 5 plus dist 5, 7. Can you still see this? Yes. Dist 3, 6 plus dist 6, 7. So dist 3, 3 is 0, 3, 7 is 9, 3, 1 is infinite, 1, 7 is 9, 3, 5 is 1, 5, 7 is 6, 3, 6 is 4, and 6, 7 is 1. So the minimum distance from 3 to 7 is 5. So we can fill in the table. How long does this take us? Well, okay, we run through all of the vertices, and for all the vertices, we look at their predecessors. How many predecessors are there in total? Well, for each predecessor there's I is a predecessor of j if there's an edge from I to j. So every edge contributes a predecessor to one of the vertices. So actually, if you have if you have a vertex that's near the end, then you don't have to consider all of the stuff before it, so it's easier. But in the worst case, so you're running over all of the vertices and you're looking at all of their predecessors, so that means you're looking at all of the edges, so it's actually going to take you time n plus m, where n is the number of vertices and m is the number of edges. So this is linear time. And the number of vertices plus the number of edges. So okay, that gives you all of the single source shortest paths. So in this case, starting at 3. What happens if you want to do it for all the vertices? Well, you could just run this for every vertex. How long is that going to take? Well, it's going to take you something like n times m. And is there a faster way to do that? Probably. Let me think for a second. So linear time is going to be the best you can do because you have to look at the whole graph. You have to look at the vertices and the edges. And so if this gives you to do all the pairs, I can't put it on the assignment because the assignment's already out. It's hard to think on my feet. So I can pause it and think about it and come back in a minute. It's easier to think when people aren't looking at me or just a camera is not looking at me. So 5 minutes wasn't enough to think of whether there's a better way of doing the all pairs shortest paths. I Googled it, but it didn't show up. But I did remember something that I wanted to say, which is in this example, it doesn't show. Well, I could make it show up. Okay, so for example, let's say that this is minus 2 instead of 1. You couldn't run Dijkstra's algorithm because you have a negative weight edge. But you know you don't have any negative weight cycles because there are no cycles because it's an acyclic graph. So it would change. This would now be min dist. So 3 to 6 plus 6 to 7 would be then minus 2. So this would become 2. So you can still do this on a graph with negative weight cycles. Otherwise, you can't run Dijkstra's. So you could get this time with Dijkstra, but you don't get it with Bellman-Ford, which is the single source shortest paths algorithm that you need to use when you have negative weight edges. Except if you have a DAG, then you can still essentially do this version of Dijkstra and get the same time because you don't have to worry about negative weight cycles, and you don't have to worry about it messing up your algorithm. So in general, in the case where you have negative weight cycles in a general graph, you have to use Bellman-Ford, and it's slower. But in a DAG, you can still achieve the same linear time that you get with Dijkstra. Okay, so that's why DAGs are cool and why you want to be able to do topological sorting, which is what we'll do next week. We'll do topological sorting and strongly connected components. Okay, so we didn't quite get, so this is a short lecture. But it's a bit late, so I'll stop it now and upload it. And I hope it's useful for the assignment. And good, okay. Talk to you next week. Have a good weekend.